So, hello again, and now we are going to calculate the same BER probability rates. So I have added this command just to show you the content of this demod file while we had some break. Maybe you needed extra time or whatever. Yes, so I'm going to remove this content now. And now we need to actually see this example of additional material for practical exercise of bachelor level course, where we specify these constellation map. So the idea here is to actually specify this constellation map so that we can, how to say it better, so that we can address each point by using its number. So for example, now, and the number is coded in the gray code. So for example, the first value, which is zeroth value, yes, zeroth element, is accordingly a value of -1, -1i. It has gray code 0, 0, 0 with this decimal notation of 0. And as you can see in this map, it is the first element. The next element is -1 plus 1i, which has the code 0, 0, 1, 0. Oh, no, sorry, I'm wrong. So it's not plus 1i, it's -3i. And accordingly, the code is 1 in decimal form, right? And so forth, we go through each of them. And this is actually index of our array which stores these values. So what we need to do now is to actually generate our new constellation, and in accordance with this plot, yes. So it's already specified here. So basically, you can just copy and paste this. How to say this array, yes, but instead I'm going to copy it from one of my sources, because sometimes from PDF file we can have some issues. Also, I want to set it all in the single line, which is quite easy to do, but actually let us try it. Yes, so I'm going to copy up to here. Yes. And see if it's okay. So we need to do so at the very beginning. So for that reason, we are no longer going to need these lines, and we'll have to rework these lines. So I'm going to erase them now, right? So I'm going to erase basically up to this point everything. And here we specify CAM16 constellation signal as a vector row. Yes, I specify them here now directly like this. Right, and I want them to be transposed to actually produce the line. So far, our code will not work because we have changed it, and we no longer have, for example, data real part. We no longer have as loss signal, and we don't even generate any signal at all. So now we have the constellation, and we can access its element by simply calling some number of this CAM16 map. For example, let me make this array. Let me clear everything also. Wait a minute, I have a mistake here. Oh, sorry. Okay, and let's call it once more. Okay, so now we have this CAM16 map, and it should be formatted in a row. We need it as a row later on here in this demodulation file. However, if you remember, we have forced it to become a row, so it doesn't really matter if we do transpose or do not transpose here, not really much, how to say it, effect to it. So we might even skip this part. At any rate, now if I want to, for example, read this point, I need to specify CAM16 map element number 15, almost the last one, yes? If I want to read this element, I need to specify element number 3, like this, yes? So, what I'm going to do now is to randomly generate one number between 1 and 16, and this is going to be our symbol position in this constellation map. So our data, instead of being generated directly as plus minus 3 and plus minus 1, is now generated rather than that as a coordinate in this constellation, number of the constellation point, which is, as you can see here, a number from 0 to 15 in gray mapping. So the number itself later on can be converted into binary form to actually know the bit contents of this signal, yes? And this is exactly why we are going to generate it, because it's very convenient to do so. And at the same time, it can be used as an address to access the coordinates in this complex plane. So for example, 15 will produce plus 3 plus 3i. And yes, I believe it was so. Yes, 15. Well, you need to know that here we have these numbers starting from 0. Yes, so at the same time in MATLAB, we can work only starting from 1, because if you try to access 0 element, it says the subscript must be positive. So actually in MATLAB, 0 matches 1, yes, and minus 1, yes, here is minus 1 and minus 1. And 15 matches 16, right? So we will have to actually subtract 1 to actually get correct gray code. But it will be the topic of near and short future. Right now, we need to actually generate this symbol. So generate symbol data, right? So as before, we are going to use rand e numbers in random number generator as before, right? And in fact, I believe this also. Wait a minute. Here we have generated binary data, and from this binary data later on we have calculated the symbols, which can be also done, but we might as well start directly by generating these symbols and converting them into binary form later on. So that's what we are going to do. Here is also one more additional help material, which also does the same way, yes, generates the random binary data and then converts it into symbols. Just for to show the diversity, we are going to do the opposite things. First of all, we are going to generate symbol data as a random integer number in range from 0 or from 1 to 16, and we are going to have in total, I believe it should not change, right? Let me double check it first. Yes, it's the same n symbol, so 1 by n matrix. Yes, so n symbols generating. So these will be random numbers from 1 to 16, and accordingly we will use these random numbers as address to access one of these points. So now we can generate our direct line of sight loss signal in CAM16 map, right? So S loss is going to be CAM16 map addressed by symbol data. Now we have this loss signal, but we still haven't real part and imaginary part. In order to make it compatible with our program, we are just going to, how to say it, specify this directly, like data real is going to be real part of this loss, data imaginary, right, is going to be imag of this loss. So now this should be completely compatible with our program which we used before. So it should work as it worked before. Let's double check if it does. So the plots have been drawn correctly. Again, we have some dimensions issues because of random number generators. It can be easily fixed by specifying hard limits, but we will not do it right now. And the error probabilities are in the same ranges. So we have modified the generation approach of the random signal. However, this also enables us to find actual binary symbols for each of these data. So, in fact, let us do it right now to find binary data as well. So binary data is calculated by converting these symbols into their corresponding binary codes. So, for example, here, right? This symbol with index 7 in decimal form is converted then in binary form by using a built-in function called dec to bin, right? So let's do it. So we are going to find binary data as dec to bin, so decimal to binary for symbol data. Yes, and in fact, because we have symbol data, well, basically from 1 to 16. So let me show you symbol data 1 to 16. Then I'm going to use bin data as a decimal to binary converter, right? So symbol data, and I'm going to get numbers like this. I am never going to get 4 zeros, and in fact, some last case I'm going to get 5 bits. However, you should know that quadrature amplitude modulation 16 actually transmits 4 bits per symbol, which comes as log 2 of the total number of possible signals, which is exactly 4. So it's impossible to transmit 5 bits in this modulation type. So we are going to make conversion for symbol data -1 instead of symbol data directly. Yes, because we start numbering in our constellation diagram starting with 0. We are forced to use numbering from 1 for MATLAB because it is just working like that. Yes, but here we can find a workaround by finding these symbols, subtracting simply -1. And accordingly, it will produce 4 bits per symbol. These are, however, unfortunately, just string type. Yes, so that means it's a text. Yes, now I don't see. Well, let's make it. We do have. So bin data 1, for example, is going to be 0, 0, right? So again, 0 it goes column wise, and accordingly, we want this to be used as so you can find it here. You can see type is char. Yes, and we want these to be numbers so we can work with them, because otherwise, for example, you will not be able to compare it with 1. Yes, or sorry, with 0, because it is not 1. But if we compare it, we want to count number of errors and compare it with 0, it will neither work. Yes, although it is a 0 bin data 3. Yes, but it doesn't show up as 0. Instead, we'll have to compare with character symbol 0, right? Which is true. So we are going to convert these characters into normal numbers which we can work with. So for that, we are going to, so -1 here, perform this test if symbol is 1. So if it is 1, then our symbols will be converted. So let's again show you with this example. So bin data is equal to 1. Now our binary data is matrix of logical numbers, but these logical numbers then can be compared. For example, bin data can be compared with, for example, 1 or 0 for that matter. Yes, it will work now. So what else we want to do is to actually make this a single sequence. Yes, so for example, this is binary data for first symbol, second symbol, and so forth, and we want them to be unwrapped into a single line. We can use for that purpose the already familiar to you method with this notation bin data like this. However, it unwraps by colon. So our symbol was in horizontal dimension, yes. So we should see 7 zeros, then 1. Instead, we are going to see 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then first 1, and then a lot of 1. So you can clearly see that it reads the first column, then it reads the second column, and so forth. What we need to do is quite opposite. So in fact, we have to transpose it to make it like this. To actually force our symbols be located in the columns. Yes, so here we have first symbol, second symbol, so forth. Now if we will unwrap this vector, this matrix into a vector, everything will be fine and we'll get the correct sequence of binary data. Yes, so bin data unwrapped, and accordingly like this. Yes, so here you can see the first symbol, the second symbol, the third symbol, and so forth. And these symbols actually match this constellation and use the same numbers. So basically, we now have gray mapping. Yes, here we used gray mapping for this. No, in fact, it's not gray mapping. Yes, you can see here that this. No, wait a minute. Everything is fine. It is gray mapping. We have only one different symbol. As I said in our course, later on we are going to talk about threadless coded modulation, which is even stronger than gray mapping way of assigning symbols, because it also uses some coding in the process, error correction coding, right? So now, since we have this taken care of, we need to actually do the same thing here. So basically we convert this line, convert decimal to binary, and here we are going to unwrap it into a single, well, row, for example. Yes, so unwrap all binary data as a row. So now we have this ideal binary data, and we actually need to do the same thing now for each of these. Actually, let us add this very same code into demodulation program. So here, once we have this demodulated data, oh, wait a minute. Actually, this index is already the answer we seek, because this index shows the number of the constellation point, which happens to be the code itself. So I did so intentionally in this constellation by assigning to specific points specific code words. Basically, or you can say that I actually was reading this constellation on purpose, starting with not this point, but with the point having the smallest number and ending with a point having the highest number. So here and here, yes, and they all go in the consequent order. So that's how I was organizing this map so that this code word in decimal form can be used as an address. Yes. So that was the whole idea of this process. For that reason, I can actually use this IDX as the symbol in decimal form. So what I need to do is now convert symbols to binary data. And I am going to convert this index IDX. As a result, I'm going to get been demodulated and demodulated here. Yes. So we add this conversion to binary form into this demodulation script. This way we will not have to do this 3 times, and instead of that we are going to add extra line here to calculate bit error rate for line of sign signal. Similarly, by comparing binary demodulated with binary data, which is perfect data. Then we need to divide with the number of symbols and the number of bits per symbol. Yes, because each symbol now contains 4 bits rather than 1. So effectively, if we transmit hundred thousands of bits of symbols, we are going to transmit 400,000 of bits, 4 times as much, right? So, and we need to take that into account by accordingly dividing correctly here. So that would be count number of bit errors, and find BER, bit error rate. So similarly, we need to do for the 2 other modulation, not really modulation, but like channel simulation scenarios, right? So that would be Rayleigh, that would be Rayleigh. Now, since in this particular case, but then again, actually, let us double check. Let's run the script and see if these values will change, right? So obviously, since we had 0 incorrect symbols for loss signal, we also have 0 errors in bits. Now, however, you can clearly see that number of bit errors is actually not as horribly large as number of symbol errors. Well, wait a minute, I actually believe this cannot be true. Wait a minute, how did that happen? Of course, because we have 4 times as much bits, and because we are using gray coding, then one symbol error produces usually 1 bit error, not always, but usually, right? And since we have now 4 times as much bits, then relatively the number of bit errors will be smaller. Yes, because only 1 of the 4 bits usually contains error, and well, considering a symbol has an error, most probably it will be just a single bit error. Sometimes, of course, it can happen that, for example, from this symbol we are going to this symbol, and therefore we are going to have 3 errors in binary code. But because of the fact that the probability of such event is strictly related to the distance between these signals, then, well, as you see, it's not really often. Now, please also note that we didn't get zeros. Yes, we don't have noise, but at any rate, there is some probability of error, which is much smaller now. As I said, because we are using gray mapping, and we actually transmit 4 times as much binary data compared to symbol data, and usually one symbol error produces 1 bit error, right? And here it's also quite possible to see that actually the situation is not so dramatically bad, yes, because we can see shapes of the clouds forming that can be detected more or less correctly. Still, there are cases of incorrectly detected symbols, right? Meaning that it introduces more than 1 error per bit, which is some statistics, right? Okay, so that is for the case without the noise. Yes, so we don't have noise. Noise is 0 right now. What we want to do now is to actually add some noise. And in order to add some noise, we need to specify signal to noise ratio. So, for example, let it be 10 decibel. Signal to noise ratio. And well, if we previously, I think, yes, let me double check it. If we previously, in the second practical exercise, used built-in function called avgn, today I'm going to actually show you how to calculate the correct noise ourselves. Yes, so for this you can study the first additional material, Symantec CAM16 channel with noise and SNR calculations. So this also introduces some generation principle, but also it tells us how to generate random numbers, noise, with specific power density called N0 divided by 2. Yes, please keep in mind that we actually need to generate complex noise as well, not specific noise for real part and specific noise for imaginary part, right? And that means we'll generate the noise twice. So how do we find these variance of the noise? Given the signal to noise ratio, we also need to find the average signal power. Well, it turns out for ideal CAM16 constellation, this average power is 10. So how is it calculated? Let's see. So if we have this, wait a minute, this CAM16 map of these symbols, what we need to do is to calculate the energy of each symbol and then average it out by dividing by the total number of the symbols. So what we are going to do is to actually take this number, yes, find its absolute value. Okay, absolute value. I didn't copy it. And square it, plus the same for the next symbol. Yes, absolute value for the next symbol, square it. So fourth, for all 16 symbols. So in short, we can write it down as the and divide by the number, which is 16. Yes, so we can find it as a sum of absolute values of CAM16 map squared and divided by 16, which is exactly 10, as I said. In fact, we can actually even use command called mean so that it does this division by 16 automatically for us. So that is how we find this signal power. And we need to do so for each of these 4 modulation type or 3 channel models, right? For loss model, we'll have 1 average power. For how to say it, Rayleigh and Gaussian will also have different, because, well, we can actually just right now test it. So what we'll have for CAM as loss, that is almost 10, yes, because we have some signal repeating, yes, and well, we generate them in uniform distribution, but still there is some, you know, possibility that some of the signals were slightly more often used than others. So it's not exactly 10, it's roughly 10, yes? So for Gaussian and Rayleigh channel, in fact, we have some attenuation, impulse response, reflected signals, which change the value significantly, yes? And for Gaussian channel, it's even below, right? So we need to consider the actual average power of the signal we have received. So for that reason, we need to calculate this power for each of these three signals before we calculate this noise. So that would be per signal loss, which is accordingly this function. So power, average power, yes, average power. Now, loss channel signal. Now, the same way it goes for Rayleigh channel signal. Here we have Rx Rayleigh. And the same way it goes for Gaussian channel model. And here also we had to use Rayleigh. Why I'm actually I'm going to calculate them all here because it isn't really related to modulation at all. Wait. This is going to be Gaussian. X Gaussian. So this noise calculation will be happening outside of these sections of the code, right? And accordingly, Gaussian channel. So each of these powers will be different, right? So that means that noise also is going to be different for each of these powers. So now we have this average power, and now we can calculate this noise variance. So let's do it. And basically, now this will be done in this section. So N0 is going to be in accordance with this formula. Wait a minute, where is that? It's here. We will not do this division by 2. We will not do the square root either. So it's going to be power of the signal divided by 10 divided by SNR divided by 10. Yes, like this. So I'm going to cut this out. This is the formula we need to actually implement here in Octave. Yes, and that is going to be our N0. So we need to divide per signal loss. Well, we could, of course, calculate just PS loss and then accordingly, copy and do some less modifications. However, calculating the average value of million points is actually quite a long operation, and we don't want to repeat it because changing noise will not change our signal. Our signal is not really affected by noise. Well, how to say it? It is affected by noise at the reception point, but the signal that you transmit at the transmitting antenna doesn't depend on the noise. So basically, what we're having here doesn't change. It has been generated here once, and for different noise values, it will remain the same. So in order to avoid calculating the same thing all over again, I have calculated them once here, and then accordingly we will use them to recalculate the noise density. Yes. So we divide it with 10 at the power of SNR divided by 10, like this, according to the formula, right? So that would be noise variance. Now, since we have this noise variance calculated, we can generate random Gaussian noise process Yes. And okay, so it's not specified here, but we already actually did so in this particular practical exercise. Here, as you can see, random normal process, right? And we needed n value. So I'm going to copy this. However, this will generate a so-called standard normal distribution process, which I need to change variance, and the variance of our noise should be set to this. More than that, actually, I will need to generate this twice for real part and for imaginary part. So let me start with that actually. Yes, so that would be real part plus 1i multiplied with the same thing. That would be imaginary part. And now I need to normalize it with this factor. Yes, and 0 divided by 2 and square root of that value. So I'm going to factor it out outside of brackets here, multiplied with sqrt and 0 divided by 2. And that is our noise signal, which we are now adding to our signal. Like this, right? Okay, we now have calculated noise for a direct line of sight signal. And now I'm going to copy this part of the code and replace it here. I missed some comment also here for some reason. Now I need to make sure that I'm using Rayleigh signal power for this. All the other is not really affected. And here, similarly, I need to, I need to, well, actually I'm going to copy and replace here with Rayleigh and here with Rayleigh. So now we have noise of the signal to noise ratio 10 decibels, right? And let's see how situation changes. The situation should change that even for direct line of sight signal, now the errors are possible. How often these errors will happen depends on the noise strength, basically on signal to noise ratio. So let's see if we get any errors now. In fact, even for direct line of sight signal, now we have quite high error probability. Of course, for Rayleigh channel and Rayleigh channel, situation became only worse, but honestly, not much worse. Yes, here we have 22% error probability versus previously 0. Yes, which is significant worsening. Here we had previously 40%, which now is 53. And here we have something like, I believe, 23% or something like that, which again is significant worsening of the situation. Now, if we change signal to noise ratio, for example, to 15 decibels, the situation should improve, right, for all three cases. But we can see that for direct line of sight signal, it improved significantly. However, no significant improvement for these cases. So what we are going now is to, instead of trying manually different values in range from 0 to 20 decibels, we are going to automate this and plot the resulting lines. So how do we do that? Actually, again, we already did so in this case. So as you can see, we counted the number of errors into some array, then we plotted these results, and we made this for loop for SNR values. So first of all, we need to specify the range of SNR values, which is from 0 with point of 0.5 to 20. Right? Not noise ratio as a range. Now we need to implement all of this code within the for loop. We don't need to do for loop for this because the noise or the signal power will remain the same. So I'm making this for loop, some specific k value, k small letter, yes, from 1 to length of SNR. Now, whenever we use SNR, here we need to actually address kth element of this SNR, like this, yes? Not all possible values, but specific values for this specific k value. Yes, so we introduced it here. Also, don't forget that you need to terminate the cycle, terminate the loop for with the end. Yes. Accordingly, now it will go through all the possible SNR values and record all the possible number of errors into corresponding arrays. So let's see how it works. Also, it's quite a good idea to actually add a message of what signal to noise ratio point is currently being processed. I'm going to add it here. Printf. Now processing SNR equal to some float number with 1 digit after comma and new line. Well, actually 3 dots and new line. And here I'm going to show SNR k value. Okay, so now it should go through all the possible signal to noise ratio values and calculate error probabilities, both symbol error probability and bit error probability for each of these values. So our code will now go through all of them. And it also outputs them, which is not exactly what I want because this takes some time. Actually, this output itself might be longer than calculations. So I'm going to put semicolons here to suppress this output. Yes. And same goes here. Let's try it once more. So yes, it has calculating all the possible SNR values. And now, for example, we can see BER loss as an array. That error probability, as signal to noise ratio increases, the error probability decreases up to 0. Yes. Now we need to plot these results for all 3 cases. For example, in this case, I'm going to use again subplot. So I'm going to make figure 4. Yes, also hold on, same way, and subplot 211, subplot 212, axis. So that is going to be title and noise immunity for 3-channel models. Where and symbol error rate, or vice versa. First is going to be symbol error rate, and the second is going to be bit error rate. And visible off. Accordingly, hold off. Now, if I make this run, Probably I will have my new window. Yes, but I want them to be horizontally, so that means I need subplot 1 to 1 and 1 to 2. Yes, so 1 to 1, 1 to 2, like this. So here I'm going to have the first plot, here I'm going to have the second plot, and some legend after all, after that, which will be positioned in some place. So, okay, let's make these plots now. First plot is going to be symbol error rate, so I will show 3 plots, yes, of all these error probabilities. So that would be plot x-axis has SNR, y-axis has log 10 of error probability. And similarly goes for the other ones. Log 10, BER, Rayleigh, SNR, log 10, BER, Rayleigh. So that would be the plot itself. Now I'm going to add X label, which is signal to noise ratio in decibels, and Y label, which is accordingly symbol error rate. Yes. Also, I wanted to add a legend. Legend, which first shows loss channel, line of sight channel, second shows Rayleigh channel, and the last one again shows Rayleigh channel, sorry. Rayleigh channel. And the last one shows Rayleigh channel, k equal to and here down to string k. Let's see if it works like that. Probably it should, but let's double check. That would be the first plot. Let's see if it works. So figure 3. Yes, unfortunately, Octave has some issues while it's calculating. The plots should have been already plotted, yes, but for some reason they have like frozen or hold off until the entire program runs out, yes, and only then these plots have been plotted, although they should have been plotted earlier, yes. So that would be symbol error probability, as you can see here, yes. For Rayleigh channel, the situation doesn't really improve almost at all. Yes, so the error probability is very high. For Rayleigh channel, the situation is somewhat better, but still is very bad. And only for direct line of sight, without these channels, without these effects of fading, is actually good enough, right? And improves as it should. We already discussed that in the lecture, if you remember, that this fading actually prevents us from reaching good signal to noise ratio, that it has some plateau effect that it will not improve. And in fact, we already tested that in the first section of our practical work, that even without noise, we still have very high error probability. So no signal strength can improve situation at all. Yes, it can even become even worse for some signal to noise ratio, but eventually at some SNR value, we are reaching some saturated level, some plateau, and cannot really change much. Well, actually, I also want to add some grid lines to this plot. Grid on. And maybe we can place this legend into some better position, because here we have plot, and if we don't really maximize the window, this legend actually is on top of our lines, which is not smooth. It would be much nicer if we could move this legend here, for example, right? So let's see help on the legend command. Help legend, how it could be done. So string property. box off. Here we can see right label text. No, that's something different. It's graphics, get set. Location. Here is the switch called location. Let's actually see if it can work automatically. Yes, so we specify parameter location and tell it to try and find best position itself. Now it will run again. As you can see, the program will now start working, but the plot will be no. No, the plot. I have scrolled and didn't see. Not yet implemented. Using northeast instead, which is default, I believe. Yes, so now we need to specify accordingly. This is going to be southwest if we want to hit this corner, right? So instead of west, let's say southwest. Actually, in order to avoid waiting time, I'm going to run this script now myself. And the legend has moved to this place where it doesn't affect us much, right? So similarly, we'll now do for the bit error rate probability. However, for bit error probability, it's often convenient on the usual thing, yes, to instead of signal to noise ratio, to use some other variant called energy bit divided by noise density, which can be recalculated from signal to noise ratio in accordance with this formula, right? So if we have this SNR in decibels, we can recalculate this energy bit by simply considering that our symbol energy is 4 times of the, so energy of the symbol is 4 times greater than the energy of the bit, right? And N0 in its turn is actually signal or noise power. Sorry, why is that happening? Noise power within a specific bandwidth. So divided by delta F. And accordingly, it can be shown by some mathematical expressions, which you can follow here, that we can basically express it with this number, where m is actually this number 4, which is number of bits per symbol. And here it's also possible to use oversampling factor the same way as we did in the practical exercise number 2. Yes. For that, I think I need to open the main exercise file called practical exercise 2 here. Yes, number of samples per symbol. So here we have oversampling factor of 7, and if we were using that filter, we should have actually calculated also this correction. But since we have oversampling KR of equal 1, this logarithm is actually 0, and we don't need to add anything. So we only need to subtract 10 logarithms of our number of bits per symbol to find this value. So actually, let's do it here before we plot it. So that would be symbol error rate versus SNR plot. And this is going to be bit error rate versus bit energy divided by noise density plot. Why this is convenient? Because you are no longer tied to specific system. Because in order to calculate SNR, you need to know what is the bandwidth of your system, what is the data transmission rate, what is the energy of the each symbol average. Well, yes, here, however, for bit, you still need to know energy of 1 bit. However, for this N0, this is usually more or less constant value, which you don't have to change, right? So it's more convenient to compare systems with different bandwidth. So consider first system has delta F1 bandwidth, second system has delta F2 bandwidth. It is very hard to compare it with SNR metric because it will depend on this frequency bandwidth. However, if we use this normalized, they can be easily compared within a single plot. So that's something for future to consider once we use some coding, right? So let us calculate this value, a bit divided by n0, by simply calculating it in accordance to formula. Log 10 of 4, yes, which is number of bits per symbol. So we calculate a bit from SNR and use it for plotting. Yes, so basically I'm going to copy this whole thing. Yes, basically even these lines. And accordingly, here I change to
Hello, Professor, can you hear me? I think you have your microphone off. I don't know if it's on purpose.
Hello? No, it wasn't on purpose.
Yes,
What?
it was off for like 5 minutes. I.
It was only 5 minutes. I was worried that it was for the whole lecture.
No. For like 5 minutes it was off.
I'm sorry. So, I'm glad it wasn't for the whole lecture. Okay, hopefully in the record it will be recorded, but probably again 5 minutes will be lost. Thank you for letting me know. So I was talking again about our holidays we will have.
I saw you were pointing the calendar, and I thought it was not on purpose, so that's why.
Okay, so yes, next week is holidays. We don't have any lectures, and on the 19th of April, we'll start talking about how we can actually correct this problem. Yes, because you can see that even without noise, Rayleigh and Gaussian channels cannot be used to transmit data. The error probability is just too high. Yes, so we'll talk about equalizers and detectors, which can be used to correct this problem with a channel. Similar, we have done so for matched filtering, which we discussed previously. Yes, we need something to compensate for this channel, and that will be the big topic of our remaining course. Yes, as you can see, once I said the power of 10, it's now working much slower. We will not wait, however. Yes, it will produce the picture that is slightly better than what we have. Yes, maybe it will go. I have closed it, but no matter. Yes, it will maybe go a little bit more in the negative 7th degree, but other than that, not much improvement from this weighting. So don't use any larger number than 10 to the power of 6. Yes, it's just impractical to get results. Too long waiting time. Okay, so are there any questions? So if no questions, then wish you nice rest in the holidays and see you then in 2 weeks.
Thank you. Have a nice day.
Thank you.
Happy
Goodbye.
holidays. Bye.